We're going to add rotations and translations to our list of transformations. We'd already looked at reflections in the previous video. So in lesson 3.1.1, you learn how to transform a shape by reflecting it, like the ice cream cones shown at right. Today you will learn more about reflections and also about rotations. So you get a resource page which looks basically like this. And it asks us to reflect across lines N and P. So I'll just zoom in here and do it on this one. So like we talked about with reflections, kind of interesting. On this one, I had to go 1, 2, 3 spots. So I'm going to go 1, 2, 3 spots. And they're going to talk about prime, which I talked about in the other video. But essentially, I know this is the original and I know this is the first image. So it gets 1 prime spot. Here are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And that's going to be my C prime. And then my A is 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'm going to go 9. And that will be my B prime. Now I'm going to go to my straight line tool to try and make these look okay. And you'll see this is my first image. And I know it's my first image because I have these primes. Now I have to do it again. So now my C is closer. So I'll go 1, 2, 3, 1, 2, 3. And hopefully you can guess what I'm going to call this. I'm going to call this C double prime. It lets me know it's my second image. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I'm going to go 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That will be my B double prime. I'm sorry. Shoot. It will be... Yeah, no, it's my B double prime. This is supposed to be A. I don't know what that is. Anyway. All right. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So there's my A double prime. And you can see that it looks a lot like the original has been moved over, which is a translation, right? When you slide something, it's a translation. So it says Amanda will label the vertices in her image triangle so it's easy to tell which vertices correspond to the vertices of the original, and the prime symbol is used. So A prime, B prime, C prime is this one. And then, like I said, we come up with A double prime, B double prime. It says, as Amanda was finding reflections, she wondered, what if I reflect a shape twice over parallel lines, investigate what happened? Well, again, it looks like we just sort of slid it over. And again, when you just slide something, it is known as a translation. So we witnessed a translation of this triangle if we skip this reflection here. By reflecting twice, it was just like translating. And again, a translation is a slide. So examine your results from A prime, B prime, C prime has been translated from the original triangle ABC. Has A double prime, B double prime, C double prime been translated from the original ABC? Yeah, it was translated, right? All right, so after thinking more about the observation, what if the lines of reflections aren't parallel? So we'll go ahead and we'll close this and reopen 3.1.2b. And we will use reflections to help us see what a rotation looks like. So in this example, what they're basically saying is reflect and reflect again, but now we have a diagonal here. So something interesting should happen here. So if we look here, same idea, again, 1, 2, 3. So I have to go 1, 2, 3. Oh, I'm stuck on this, sorry. So that'll be my F prime. G was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. By the way, if you're thinking, why don't you just go to F and count 8 more? It's not a bad idea. All right, and E, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And I get E prime. And again, what's going to happen now is we're going to rotate it across this diagonal. So again, it's up to you if you decide to go over and down or diagonally. I don't really care. I'll just go diagonally. So 1, 2, 3, 4. So I'll go 4 more. 1, 2, 3, 4. This will be my E double prime here. I had to go 1.5, so I'll go a half and 1. I'm sorry, 1.5, so a half and 1. Yep, that's my G double prime. And F, 1, 2, 3, 4, 5.5, so a half. 1, 2, 3, 4, 5. So this will be my F double prime, and again I will go ahead and use this. So hopefully you see again that you can reflect, and it's fine. So, but here's the thing, if I look at point P, doesn't it kind of look like I just slid, just ignore this triangle, doesn't it look like I took this original and I just rotated this whole thing to this double prime? So now we've dealt with all three, right? We said that there was transformations. That's what we were going to talk about in this chapter. We started with the first one, which was reflections. Then, earlier in this video, we reflected twice across parallel lines, and we got a translation, which was like a slide. And now we've reflected once across a line and then once across a non-parallel line, and it looks like we have a rotation. So these are going to be our three different transformations, and again, these are known as rigid transformations. They keep the same shape and the same size. In Integrated 2 next year, you're going to learn about dilations, where it's like your pupil dilating, where the sizes don't stay the same, and it's not a rigid transformation. So Amanda noticed that when reflecting lines are not parallel, it was a rotation. Again, for example, the diagrams at right show what happens when this ice cream cone is rotated. Again, this is up and it gets rotated over, so now this is up. So it says in part A, the center rotation is at point P, the point of intersection of the lines. So essentially what they're saying is, hey, look, if this should have kind of the same thing as that, and that should have the same thing as that, and that should have the same thing as that. So we kind of get that same look to that center there. And a lot of kids think that you need a lot of help when you rotate, but rotating is actually a pretty simple process. So let me go ahead, and on this one it says the rotation of triangle EFG is an example of a 90-degree clockwise rotation. Again, it's like a clock, the way a clock works. So if this is the top of the clock, this would be the way the clock moves. This is clockwise. This would be 90 degrees. This would be 180 degrees. And this would be 270 degrees. And this would be 0 or 360, right? Because this is known as clockwise. So hopefully you guys know this already. Hopefully I'm not teaching anything right here, but just in case we don't. Counterclockwise means we go against the clock. I wrote counter twice. That's not what I wanted to do. I wanted to write clockwise. So counterclockwise means we go against the clock. So think about it. If this is the top of the clock, or 0, 360 degrees, now this will be 90 degrees because we're going against the clock. This will be 180 degrees. This will be 270 degrees. So a couple things I want to point out. Whether you go clockwise or counterclockwise, the 0, 360 doesn't change and the 180 doesn't change. But the 90s switch and the 270s switch, right? So just important to keep that in mind. So this was a 90-degree rotation, right? We went from this being the top to 90-degree rotation to this being the top, which is what we're going to kind of look at when we do these, there being a quote-unquote new top. So it says the rotation of triangle EFG in part A is an example of 90 degrees clockwise rotation. The term clockwise refers to a rotation that follows the direction of the hands of the clock, right? This means it goes in clockwise. A rotation in the opposite is called counterclockwise, which we just discussed. So it says perform the rotation again, noticing the starting and ending orientation of the plus. Use 315C. So I'm a little confused what it's asking me to do. Let me pause this and kind of look and figure out what I must have missed the question. Okay, so I see my confusion. They give us the shape and they don't ask us to do anything with it, but I didn't realize that part E was cut off here, so I apologize for that. So let's go ahead and get to part E of this. So if I open this, I think I'm on this one. Oh, there we go. So it says on the resource page, rotate polygon 90 degree counterclockwise. So now what I'm going to have to do is I'm going to have to go back to the last one so I can get my shape, and I'm going to go 90 degrees counterclockwise. So obviously when I downloaded this stuff, I made an error on that, and I apologize for that. So here we want to turn this thing 90 degrees counterclockwise, and we'll do more of this later, and I will tell you, I know kids struggle very much with this, but let's just look at the shape. I know this is up, all right, actually, and I know this is down, and I know that this is left, and I know this is right? Well, think about it. If I go 90 degrees counterclockwise, that means that this, now I'll change colors here, think about it. Wouldn't this be up now? And if you turn your head, if this is up, isn't this down? And wouldn't this be left? And wouldn't this be right? So that's what we're going to do. We're going to just sort of count these points, and we're going to kind of go in the direction they're at, just again to show that you don't need graph paper. And again, I'll tell you, a lot of kids struggle with this. So let's pick this point. This point right here, I go up 1, 2, 3, 4, 5, 6. Well, if I want to get the same point, I need to go up 6. 1, 2, 3, 4, 5, 6. Now you might be saying, well, Alvaro, you didn't go up, you went left. Well, yeah, this is my new up because I want this to be up because this is how I'm rotating this thing, right? So that's my new up. I'll change colors on these. What if I want this point? I didn't change colors. What if I want this point now? I'm going to go right 1, 2, and I'm going to go up 1, 2, 3, 4, 5, 6. Well, now I'm here. Think about it. I want to go right 2. This is the new right, 1, 2, and then I want to go up 6. So that point would go there. What about this point? This point, I would go right 2 and up 2. Again, this is my new right, and this is my new up. If I want to get this point, I would go right 1, 2, 3, 4, and up 2. So I'll go right 1, 2, 3, 4, and I'll go up 1, 2. To get this point, I just went right 1, 2, 3, 4. So I'll go right 1, 2, 3, 4. I don't need to go up or down. Again, you can say I'm originally going right, so then I'm going to the new right. Originally I'm going right and up, so I'm going the new right and up. You can see how that works. And the last one's easy, right? To get to here, I didn't do anything, so to get to here, I won't do anything. I meant to make that this color. I keep not doing it. There we go. All right, now just to finish this off, what does it look like to go 90 degrees counterclockwise? Well, I'll just connect these dots. And you can see this looks pretty good. It definitely looks like I went 90 degrees counterclockwise. I just sort of laid it on its side. And again, I needed a point to rotate for it, and they gave me that point. So that's what's going on when we do these rotations. You'll see more of that in these videos. And again, I know some kids struggle with it and they go straight to the graph paper, which is fine. I just think it's a lot easier to do it without graph paper, and I think it's a lot more precise to do it without graph paper. All right, so Amanda continues moving figures. The diagram to the right shows A, B, C, D. Look carefully at the correspondence between the vertices. Can you rotate or reflect the original square to make the letters correspond as shown? Well, it sure looks like we reflected across the line right in the middle. That B went a little bit, the A went further, the C went a little bit, the D went further. So it looks like we reflected across this line. It says this time Amanda rotated A, B, C, D by 180 degrees, about the point. As shown at right. Copy the diagram for both squares at the point. Well, think about it. If we went 180 degrees, this was up. Well, now my new up is going to be way down here, right? And this was left. Well, now my new left, well, actually, I guess it'd be easier to do down first, wouldn't it? I think it'd be easier to do down first. So if this is my down, my new down is now up here, right? This is my original left. This is my original right. But if this is up and down now, if you turn your head completely upside down, you can see that this would be my new right, and this would be my new left. As a matter of fact, I'm going to put primes, just to let you know that these aren't the originals. Now let's look at the shape and see what would happen. Well, this shape, if I rotated 180 degrees, I had to go right and down. So I have to go down and right. Oh, I'm sorry. Give me a second. I've confused myself. I see my problem. I'm sorry. I was starting from this point, not from here. I need to start from here. So to get to this point, I originally went left and up. So now I need to go new left and new up. So this would be my B prime. To go to the A, I had to go left a lot and up a little bit. So now I'll go new left a lot and up a little bit. So this will be my A prime. To get to my C, I went left a little bit and down a little bit. So I'll go new left a little bit and new down a little bit. This will be my C prime. And to get to D, I had to go left a lot and down a little bit. So I'll go left a lot and down a little bit. And this will be my D prime. So there's definitely easier ways to sort of conceptualize than what I just did, but I wanted to kind of show that up, down, left, right thing. And again, I screwed up originally because I didn't start at the point of rotation, and that's where you want to start, is at that point of rotation. All right, so it says reflections, rotations, and translations are called rigid transformations. Rigid transformations don't change any of the measures of the angles nor the side lengths. Same shape, same sides. The word transformation and translation sound alike. They can be easily confused. Again, transformation is the main thing. Translation is a type of transformation. All right, so examine A, B, C, and A prime, B prime, C prime, and the graph at right. With your team, describe at least 2 different ways that we could get there. Well, we could have reflected across and then moved it down, or we could have moved it down and then we could have reflected across, right? There's at least 2 different ways. There's several other ways. As a matter of fact, an infinity of ways that you can do that. Are there always multiple ways to describe any transformation? Yeah, I think there probably are. All right, 318. Consider what you have learned about rigid transformations. Would a series of rigid transformations preserve the area of a polygon? Yeah, it's going to be the same shape, the same size. All right. If 2 polygons have the same area, are they always image a series of rotations? Well, no. Like here we go. Let's say that this is a 4 by 4. This has an area of 16. And let's say this rectangle is 2 by 8. This has an area of 16. And they're clearly not the same shape and same size. So I would say no there. It says verify your answer in part A by calculating the areas of the original triangle EFG and E double prime, F double prime, G double prime in problem 315. Then calculate the areas of both the blocks in 315. So I guess let me set that up. Okay, so for right, these triangles should have the same area. So it's obviously base times height divided by 2. So here I get 8 times 3 divided by 2, which is 24, divided by 2, which is 12. This one, I'll make this my base of 8, my height of 3. So 8 times 3 divided by 2, which is obviously also 12. So yeah, we do have the same area there like we suspected. And then sadly I've lost this one, so I need to set this up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and then there we go again, 6, 12, 14, 16. So the areas are the same. They are indeed rigid transformations.